Discrete random variables. What is a discrete random variable? In previous chapters, we've described the probability of events by using words. The probability that I throw a stool because no one will shut up, or the probability that I get fired because I threw said stool. You know, things like that. Yeah, by the way, the second one, the probability I get fired because I throw a stool, 100%. Perfect. Guaranteed to be fired. But anyway, we used a lot of words. And you know when I was writing P of, and I was having to write words in those parentheses, and I was like, gosh, it's so much easier with symbols than it is with words. Well, see, it's much more convenient to use numbers or symbols, and that's what we're going to start doing. So a random variable represents in number form the possible outcomes which could occur for some random experiment. If you're ever reading a paper, an abstract about, oh, when they did a test, oh, it's shown that if you eat too many grapes, you get cancer or some bull like that. You'll notice if you're reading the actual paper, somewhere in parentheses, it'll say n equals, and there'll be a number. And they're letting you know how many people there were in the test. So then they could say probability that n equals 10 or something like that is, oh, that means probability that 10 out of the total number did something. So we use symbols because it's just easier than saying all those darn words. Mathematicians don't want to write as much, and we like our numbers. So a discrete random variable, capital X, and it is important that it's capital, has a set of distinct values, and these values would be little x's, x1, x2, x3, dot, dot, dot. So in our class, we'll consider only a finite number of outcomes, all the way out to xn. Can this stuff be done with infinite outcomes? Yes, but those people get paid a lot more than me. I don't know how to do that stuff. For example, capital X could be the number of students that walk to school, or the number of red marbles in a bag. What did both of these numbers have in common? Say it louder. They're whole numbers. That's what makes them discrete. You can't have 1.5 people walking to school. If you do, that's usually a crime scene, right? No, this is whole things. That's what makes it discrete. To determine the value of a discrete random variable, we need to actually count those things. I think it's called a counting principle, maybe. A continuous random variable, capital X, could take possible values in some interval on the number line. For example, X could be, see, this is continuous random variable. X could be basically anything with a decimal. Lengths of hair, or volume of coffee. Measurements are usually continuous random variables. Discrete random variables can't have things land in between. I go, how many of my students passed? I can't say 23.4 of my students passed. That doesn't make any sense. What's the average, what's the hair lengths of my students? Well, what's the shoe sizes of my students? Discrete. What's the leg length or foot length? Actually, that's going to be continuous. Because the probability, I like how we're doing this, the probability that your foot and someone else's foot are 100% exactly the same length, very small. So if it can be counted, discrete. If it's measured, continuous. That's what it says. Determine the value of a discrete random variable, count. Determine the value of a continuous random variable, measure. There we go. Probability distributions. Sorry, I'm scratching my nose. For any random variable, there is a corresponding probability distribution. It describes the probability that the variable will take on particular values. So let's just say a die, standard die, 6 sides, right? What you could say is you could define capital X to be the value on the side of the die. Then the Xi's, X1, X2, X3, yada, 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 those would be the values it could take on. So capital X could be 1 or 2 or 3 or 4 or 5 or 6. Make sense? And then a probability distribution would list out all of the values it could take on. Well, if it's a fair die, every one of those numbers is 1 over 6, right? This is the way you're going to be writing this. Now, I know that looks weird that capital X equals little x, but if in the event that I'm talking about the die that we were just talking about, we would say, what you would say is let capital X equal the number on the die, something like that. So then I could say something, the probability that x equals 2 is 1/6. That right there says the probability I roll a 2. See, it's just so much easier to use symbols and numbers than it is to write it all out in words. And of course, capital X, it wouldn't matter if capital X was 1 through 6, it doesn't matter which one you pick. If it's a fair die, they all would have had 1/6, but that's what that says. The probability that the number on the side of the die is 2 is 1/6. That's what that says. What do we have here? When you're tossing 2 coins, if you're trying to count the number of heads, you only have 3 options. There could be 0, there could be 1, there could be 2. So you would say, let capital X be the number of times I found a heads. And it would either be 0, 1, or 2. Okay. If you're flipping 2 coins, technically there's 4 outcomes. We've done this before. Like if you do a 2x2 grid, you have 4 outcomes. So the probability that x equals 0 is 1/4. The probability that x equals 2 is 1/4. That means the probability that x equals 1 has to be the rest of the 1/2. Okay. We can show off these probabilities in 2 different kinds of graphs. We can either use a spike graph, or we could use a column graph. Notice in that column graph, the columns do not touch. They don't touch because this is discrete. There's nothing in between the numbers 0 and 1. Okay? Just for IA purposes, when you go to graph your stuff, if you're going to use a bar graph and it's not a continuous variable, please don't let your bars touch. That's the kind of thing that shows you don't understand, and I would have to take credit away for that kind of stuff. Or you could just use a spike graph. That one's really easy. It's just a line with a ball on the end of it, We cool with these ideas? That's all our vocabulary and stuff like that. Structures. We're good? Then let's practice. Like I said, it's going to be very short notes today. A supermarket has 3 checkout points, like 3 checkout lanes, A, B, and C. A government inspector checks the weighing scales for accuracy at each checkout. If a weighing scale is accurate, then Y is recorded, I'm assuming for yes, and if not, N is recorded for no. Suppose the random variable capital X is the number of accurate weighing scales at the supermarket. Okay. So for part A, when it says list the possible outcomes, well, we are trying to figure out what all the possible outcomes are. Unfortunately, there are 3 lanes. That means there are 8 possible outcomes. Yeah. Why 8? Because that is 2 to the 3rd power. Because every one of the lanes is either a yes or a no. So there are 2 to the 3rd power results. We have to list out all the possible results. It means we have to find all 8 combinations of yeses and nos. Here we go. What are my lines? A, B, and C. So these are possible outcomes. Lane A, lane B, lane C, and capital X is supposed to be the number of accurate scales. Let's say it's a worst case scenario. All 3 record a no. That is the only way that X equals 0. Why? Why what? Why does X equal 0? X stands for the number of accurate scales. So it says, suppose the random variable capital X is the number of accurate scales. Now we could say that lane A works, but the other 2 don't. So there's 1 working scale there. Well, how many different ways could I have 1 working lane? How many different ways could I have 1 working lane? 3, because there's 3 scales. So that little y there could shift around. Going to have to extend these columns. All right, well, what if there's two working scales? And instead of saying two working scales, 'cause I feel like that's a little harder to do, what if we said one non-working scale? See, we started with three not working. All three of these results are two not working. How about one not working? So that would start with this. So now there's two scales. And that n could shift places twice. And it could be in the middle here, or it could be at the front. And then, of course, best case scenario, all three, oh goodness, all three scales work. Those are the possible outcomes, the 8 possible outcomes. I'm sorry? It is permutations. But here's the nice thing. In our class, in SL, we don't worry about permutations. We're going to worry about combinations. So for us, every time there was one working scale, that is an x equals 1, and that makes us happy. So even though there are 8 different ways that could happen, we're going to concentrate on the x equals 1 or x equals 2 or x equals 3 kind of stuff. Okay, what is the next one? It says describe using x the events. Okay, so for part B, describe using x. One accurate scale. Guess what that would look like? There's one accurate scale. Ta-da. That's BI. What would at least one accurate scale look like? Greater than or equal to 1, but that would be 1, 2, or 3, right? But so you could also say x is greater than or equal to 1. They say the same thing. Greater than or equal to 1 is easier, but it's important that you understand that means that was 1 or 2 or 3, and when we string our statements together with ors, what are we supposed to do? No, in probabilities. Like if I say probability of A or B, you add them. So if I say the probability that x is greater than or equal to 1, that's actually 3 different probabilities that must all be added together. This is why we use the calculators, because it'll do that for us automatically. It'll just add the 3 together for us. Part C says find the probability of, or find the value of P of x equals x, which means the probability of each x value occurring. Okay, so for part C, what it's asking is, what is the probability that x equals 0? What is the probability that x equals 1? What is the probability that x equals 2? And what is the probability that x equals 3? That's what it's asking for. So you already know those 8 outcomes. What's the probability that x equals 0? 1 out of 8. What was the probability that x equals capital 1? I mean, capital X equals 1. I'll be okay. 3 out of 8. It is a credit card company. Huh. What's the probability capital X equals 2? 3 out of 8. And since all probabilities have to add up to 1, what is the probability that x equals 3? 1 out of 8. There you go. It says graph the probability distribution against x as a probability column graph. It just wants us to draw a column graph. That's all it wants. Okay. Well, my probabilities are 1/8 and 3/8, and that's it. You okay back there, Gavin? Is this part D? Down here are my x values. Actually, you know what? Let's do it like this. Capital X equals active panel, please catch up, equals fancy X. There you go. Because it's script. And since capital X and lowercase x pretty much look the same, We'll use fancy x for the little ones. What are the values that it could take on? X could be 0. This is going to drive some people mad. 1, 2, or 3. Capital X equals fancy X, where fancy X could be the numbers 0 or 1 or 2 or 3, Gavin. Yes, I did. And the probabilities are either 1/8 or 3/8. So I just went 1, 2, 3, 4. 1/8, 2/8, 3/8, 4/8. And these are the probability that capital X equals fancy X. And legitimately, you just draw some bar graphs. So probability that equals 1, equals 0 is 1/8. The probability of 1 and 2 are exactly the same, 3/8. Go for it. And X equals 3 is 1/8 again. There it is. That's legitimately it. It is pretty darn simple. For now.